Good morning. Today I will talk about some recent results from our MBH simulations on the dynamical evolution of massive black holes or massive black hole pair in a circumnuclear disk. So I will start with a brief introduction to the topic. So then I will check. Pronto? I will start with a brief. Okay. I will start with a brief. Okay. I will start with a brief introduction to the topic. Then I will focus on our results, focusing on the dynamical evolution of massive black hole pairs in both gaseous or stellar disks, and on the disks. Okay, and on the possibility of accretion processes around the two supermassive black holes during their evolution. Then at the end I will show you our conclusion and some open issues. The different phases of the evolution of massive black holes, or the massive black holes pairing during a gas-rich major merger, have been highlighted today by Lucio. So I will focus my talk on starting with the two supermassive black holes are at the separation of the order of 100 parsec when they are embedded in a circumnuclear disk. The initial conditions of our simulations are a central massive black hole of 4 million solar masses placed at rest at the center of a composite structure composed by a circumnuclear disk and embedded in a stellar bulge. Our circumnuclear disk follows a Messer profile with a total mass of 10 to the 8 solar masses and a radius of 100 parsec. The circumnuclear disks can be both composed by stars or gas, and for the gaseous component we have a pure adiabatic evolution. Our stellar bulge follows a Plummer model with a total mass of 7 times 10 to the 8 solar masses and length scales of 55 parsec. In every simulation, we put a secondary massive black hole, the same mass of the primary, at the initial separation of 50 parsec from the center onto an eccentric orbit with eccentricity 0.7. And the secondary massive black hole can be both on a co-rotating or on a counter-rotating orbit with respect to the disk. In this figure, in the upper panel of this figure, we show the relative separation between the two massive black holes as a function of time. We can see that, the red line refers to massive black hole pairs embedded in a stellar disk, in a pure stellar disk, while the blue line refers to massive black holes in a gaseous disk. We can see that in the two cases, the dynamical evolution is quite similar, and the two massive black holes can form a binary at a separation below 10 parsec in less than 10 to the 7 years, 10 megayears, and they can reach a final separation of the order of 1 parsec that is approximately the spatial resolution of our simulations. We can see that during their evolution, the orbital eccentricity of the pair decreases down to a final value of the order of 0.1. Okay, so the process that drives this circularization is due to the different effects that dynamical friction has onto the orbiting massive black hole at different phases of its orbit. And these different effects are highlighted by the different relative position between the overdensity waves excited by the supermassive black hole and its path. And these overdensity waves can be observed both in gaseous or in stellar disks. In this figure, the green line is the black hole trail. In particular, when we observe the pericenter passage of the secondary massive black hole, the massive black hole has a velocity that is larger in modulus than the rotational velocity of the disk, and so it excites a over-density wake behind its trail. In this case, the over-density wake breaks the supermassive black hole, removing its orbital energy and angular momentum. On the other hand, at the apocenter, well, the supermassive black hole, the disk is moving faster than the supermassive black hole, so the over-density wake is dragged in front of the supermassive black hole motion, and it can increase efficiently the supermassive black hole angular momentum. These two different effects of the dynamical friction are so that the relative separation in the orbital energy of the pair, the supermassive black hole pair, decreases faster than its orbital angular momentum, circularizing the orbit. Okay, now let's focus on some higher resolution simulation when our spatial resolution is of the order of 0.1 parsec, and the disk is only gaseous, and the two massive black hole can accrete gaseous bound particle during the revolution. In the upper panel of the figure, we can see the relative separation between the two massive black holes as a function of time, and also in this case, the two massive black holes reach a separation of lower than 10 parsec, and they can form a binary, and the final eccentricity of the pair is of the order of 0.1 parsec as well as in the lower resolution simulations. But in this case, the two massive black holes cannot reach a separation of the order of our numerical resolution and seems to stall. The stalling is related to the formation of a central core in the nuclear disk that can be observed both in the surface density profile and in the cumulative mass profile of the disk. The different lines refers to different times in our simulations, and in particular the black line refers to our initial condition, while the green line refers to the density profile after 7.5 megayear from the beginning of the simulation. And we can, the dotted vertical lines refer to the position of the secondary massive black hole at the different times. And we can see that the core forms well before the secondary massive black hole reached the central region of the disk. So this core formation can change the dynamical evolution of the secondary massive black hole, causing the stalling of the binary. We will see in the next slides that the total lacking mass in the inner region of the disk cannot be accreted by the two supermassive black holes, because during the simulation they accrete only a small fraction of their mass. So we can define two different regions in the core. A region for a radius smaller than 1 parsec, in which the core is formed due to the accretion processes on the central massive black hole, and another region between 1 and 10 parsec, in which we need a dynamical process in order to form our observed core. And this if we look at the central region of the disk, this plot has a scale of 10 parsec, we can see that, as saw in the precedent slides, that the perturbed region by the secondary massive black hole at the pericenter has an overdensity wake behind the secondary massive black hole, trigger an overdensity wake behind its trail. If we look at the temperature map in the same region, we can see that the perturbed gaseous particles are also hotter than the unperturbed region, and they have also a tangential velocity that is higher in modulus with respect to the unperturbed region. So, at the pericenter, the secondary massive black holes, the secondary massive black hole eats the gas in the central region and increases its kinetic energy and its thermal energy and its angular momentum, so that the gas can escape from the central region of the potential well forming the core. I want to notice that this process is efficient only for secondary massive black hole that starts on a highly eccentric orbit and not on a quite circular orbit as shown by Lucio this morning. On the other hand, if we observe the dynamical evolution of secondary massive black hole onto an eccentric, initially counter-rotating orbit with respect to the disk, we can see that also in this case, the two massive black hole can form a binary for separation smaller than 10 parsec or so, and also in this case, the two massive black hole stall at a separation over the order of 5 parsec, but on the other hand, the final eccentricity is larger than in the co-rotating case, and is of the order of 0.5, 0.4. A peculiar feature observable in this simulation is that if you look at the angular momentum normalized to its initial modulus, so starting from -1 because the secondary massive black hole is counter-rotating with respect to the disk, we can observe that the angular momentum in modulus decreases down to a value of 0 when the secondary supermassive black hole is instantaneously on a radial orbit, and then start to increase and begins positive, so that after 3 megayears, the secondary supermassive black hole starts to co-rotate with the disk. This process is due this process is due is caused by the dynamical friction process, the dynamical interaction between the secondary supermassive black hole and the rotating disk. At the apocenter, in this simulation, when the supermassive black hole is counter-rotating, the overdensity wave is formed behind its trail, so eroding its tangential velocity until the massive black hole lose also until the tangential velocity is 0, and then the supermassive black hole is accelerating in the same direction of the rotation of the circumnuclear disk, becoming co-rotating with the disk. Also, in this simulation, we can observe the formation of a core in the inner region of the disk, but on a longer time scales. But at the beginning of the simulation, until the secondary supermassive black hole is still counter-rotating with the disk, we can observe a central transient cusp for separation smaller than 1 parsec, and we will see that this transient cusp will be accreted by the primary supermassive black hole in the center of our disk. And then when the supermassive black hole begins to rotate, a central core forms as well in the other simulation. Okay, now, what about accretion events onto the two supermassive black holes? In this slide, I present the mass of the supermassive black holes normalized to their initial mass as a function of time. And the red line refers to the simulation with the secondary supermassive black hole counter-rotating with respect to the disk, while the black line refers to the other one with a secondary co-rotating with the disk. The solid line refers to the initially to the central supermassive black hole at rest in our structure, while the dashed line refers to the initially orbiting supermassive black hole. So we can see that after a few megayears, the central supermassive black holes can accrete a fraction of 10% or so of their initial mass, and the co-rotating supermassive black hole can accrete a fraction of 5–6% of their initial mass, while the counter-rotating is initially accreting at a lower ratio, so that the final mass is increased only by a factor of 0.4 or so. In the case of a co-rotating supermassive black hole, we can study the Eddington ratio evolution as a function of time, and we can see that until the supermassive black hole is on a highly eccentric orbit, the Eddington ratio is lower, and its weight is highly variable until the supermassive black hole is quite circular, so that when the relative velocity between the secondary supermassive black hole and the disk is smaller, and the Eddington ratio is similar to the one of the central supermassive black hole. The mean Eddington ratio of the initially orbiting of the secondary supermassive black hole is 0.4 in all the simulation, while if you study the first part of the simulation when it is eccentric, the mean value is 0.3, and the later accretion processes as an Eddington accretion mean value of an Eddington ratio mean value of 0.45. The situation is more interesting for initially counter-rotating supermassive black hole, and we can note that the Eddington ratio is much more smaller for until the supermassive black hole starts to co-rotate with respect to the disk at a time of the order of 3 MegaYears or so. So if we look at the average value, the Eddington ratio before the supermassive black hole starts to co-rotate with the disk is 0.1, while after the supermassive black hole is co-rotating with the disk, the mean Eddington ratio is 0.45, so it increases of a factor of 0.4, 0.5, 5, sorry. So, our conclusion on this work is that in all our simulations, the supermassive black hole can form a binary. The supermassive black holes can form a binary in less than 10 to the 7 years, but if we study the simulation with high resolution, with a secondary supermassive black hole on a high eccentric orbit, and with the possibility, and with the massive black hole that can accrete gaseous bound particle during their simulation, so a nuclear core can form in the inner part of the disk, and so it could there could be a stalling problem also for a gaseous background. The two massive black holes circularize its orbit inside the gaseous or a stellar circumnuclear disk, and seems to regardless to the composition of the disk, if they are co-rotating, they are initially co-rotating with respect to the disk, while if they are counter-rotating with respect to the disk, there is this kind of angular momentum flip, so the massive black hole starts to co-rotate with respect to the disk after some time. And at the end, we predict some variable accretion processes during the spiral onto the two supermassive black holes, and in particular, the variability is higher for the initially orbiting supermassive black hole. But I told you that the possibility that a nuclear core can give us a last parsec problem, but some other, some future step can be done, and in particular, in presence of gravothermal instabilities and of presence of non-axisymmetric structures as nuclear bars or so, the nuclear core can be refilled with gaseous particles so that the two massive black holes can reach lower separation. In particular, if we have denser or more massive disks, as the one described by Lucio, or colder disks, as the one described by Scala in his work. And also, if we have a supernova explosion in our circumnuclear disk, probably they can mix the gaseous distribution in the disk, refilling in principle the inner region of the disk. Well, we can have gravothermal instabilities also in our simulation with a less massive disk. In particular, if we allow the gas to cool down by radiative cooling, but in absence of any kind of local heating source, as for example supernova feedback, given our high densities, the circumnuclear disk can cool down and form a very peculiar structure with clamps all over the disks, and this structure is not representative of an observed circumnuclear disk, so we need to run a simulation with radiative cooling and some form of some sources, some heating sources, as for example, supernova feedback together. Thank you.